Beyond keywords, how vector search powers our digital world. Chapter 1. The frustration of keywords and the dawn of semantic search. Imagine standing in front of a sprawling, disorganized library. Not a traditional library with neat shelves and dewy decimal classifications, but one where every book is simply piled onto an enormous floor, with no order whatsoever. You need to find a specific book, say, one about the history of artificial intelligence. Your only tool is to shout keywords into the massive hall, hoping someone, or something, will pick out exactly what you've uttered. Artificial intelligence, you might call, or perhaps AI history. This, in essence, is how much of our digital world used to feel, and in many corners still does. From the earliest days of the internet, finding information has largely relied on a simple principle: matching keywords. You typed a word or phrase, and the search engine or database diligently returned documents containing those exact words. It was revolutionary for its time, pulling needles from haystacks faster than ever before. But as the digital haystack grew from a small pile to a sprawling mountain range, the limitations of this approach became increasingly apparent. Consider Sarah, a nature enthusiast planning a weekend hiking trip. She visits an online outdoor gear store looking for a backpack. Sturdy backpack, she types into the search bar. The results pop up: lightweight fashion backpacks, small school bags, even a few toy backpacks. None of them are suitable for her intended purpose, carrying gear for a multi-day trek through rough terrain. She tries variations: durable rucksack, then backpack for long hikes. Still, the system struggles. It pulls up many irrelevant items because it doesn't truly understand what sturdy, long hikes, or rucksack imply in the context of her unspoken need for a load-bearing, comfortable pack. The frustration mounts. Sarah's dilemma highlights the fundamental weakness of keyword search: it's literal. It's excellent at finding exact matches, but it utterly fails at grasping nuance, context, or the underlying meaning of our words. The English language, and indeed all human languages, are full of synonyms, like car and automobile. Ambiguity, think of bank. Is it a river bank or a financial institution? And phrases that carry deep implicit meaning beyond their individual words. A traditional search system doesn't know that comfortable walking shoes means something entirely different from shoes comfort walk, even though they contain similar words. It's like trying to have a meaningful conversation with someone who only understands a dictionary, not common sense or context. For decades, we've tolerated this. We've learned to phrase our searches carefully, using multiple synonyms or specific technical terms, hoping to hit upon the magic combination that unlocks the information we seek. We've developed a kind of digital sixth sense for how to talk to a machine that doesn't truly listen. But the world has changed. The sheer volume of data being generated every second: text, images, videos, audio, is astronomical. We're drowning in information, yet often starved of true insight. At the same time, artificial intelligence, or AI, has moved from the realm of science fiction into our daily lives. From smart assistants that understand our spoken commands to recommendation engines that suggest movies we'll love, AI is slowly but surely bridging the gap between human intent and machine understanding. And at the heart of this new era of intelligent information retrieval lies a powerful, yet often unseen, technology: vector search. Imagine that vast, disorganized library once more. Now, instead of shouting keywords, imagine a magical system that quietly reads every single book, every article, every image, and every audio tape. Then, it transforms each of these into a tiny, unique numerical fingerprint, a secret code not made of letters, but of numbers. Furthermore, this system is so clever that it makes sure that all the books about artificial intelligence have similar numerical fingerprints, and all the books about cooking pasta have their own distinct, but similarly grouped, fingerprints. When you then ask for history of AI, your query is also turned into a numerical fingerprint, and the system instantly finds all the most similar fingerprints in its collection, regardless of the exact words used. It finds the meaning. This numerical fingerprint is what we call a vector, and the process of creating it is called embedding. Vector search is essentially finding points, vectors, that are close to each other in an abstract digital space, where closeness equals semantic similarity. It's how AI systems are learning to understand us, moving beyond keywords to decipher the true meaning behind our queries. No longer are we limited to searching for what we say. We can now search for what we mean. This fundamental shift is quietly powering much of the intelligent technology we interact with daily, from getting personalized shopping recommendations and accurate answers from chatbots, to sifting through millions of images or even discovering groundbreaking insights in scientific research. Over the coming chapters, we'll demystify this powerful technology. We'll explore what these vectors and embeddings truly are, how data from text to images can be transformed into them, and how computers quickly find connections between billions of these numerical fingerprints. We'll discover the clever tricks and algorithms that make vector search incredibly fast and efficient, and we'll look at fascinating real-world examples of how it's already reshaping our digital landscape. Finally, we'll peer into the future, considering the challenges and the immense potential of truly semantic understanding. Prepare to go beyond keywords and discover how vector search is powering the next generation of our digital world. Chapter 2, the core concept. What exactly are vectors and embeddings? In our last conversation, we talked about the frustration of keyword searches and how computers struggle to understand the nuances of human language. We hinted that vector search is the solution by helping machines grasp the meaning behind our words. But how does it do that? The answer lies in two core concepts: vectors and embeddings. Don't let these terms intimidate you. They're simpler than they sound, especially when we use a little imagination. Let's start with vectors. Forget complicated math for a moment. At its most basic, a vector is simply an ordered list of numbers. Think of it like a set of coordinates that tells you exactly where something is located in a particular space. Imagine you're trying to describe the location of your favorite coffee shop on a city map. You might say it's 3 blocks east and 5 blocks north of a central point. We could write these instructions as a list: 3, 5. This pair of numbers is a vector. It precisely defines a single point on a two-dimensional map. Now, what if we wanted to also include the coffee shop's altitude? Perhaps it's on the second floor, a height of 1 in your building system. Your location could then be 3, 5, 1. This is now a vector defining a point in three-dimensional space, where the third number represents height. We can apply this idea to more abstract things too. Think about a recipe. Instead of describing it as some flour, a bit of sugar, and a few eggs, you could quantify it. 2 cups flour, 1 cup sugar, 3 eggs. This specific combination could be represented as a vector like 2, 1, 3. Each number defines the quantity of a specific ingredient. If you wanted to include butter, it might become 2, 1, 3, 0.5. What makes a vector special, beyond just being a list of numbers, is that it gives us a precise way to represent something, whether it's a location, a recipe, or, as we'll soon see, a complex piece of data like a word or an image. This brings us to the idea of dimensionality. When we talked about 3, 5, that was a two-dimensional vector. 3, 5, 1 was three-dimensional. Each number in the list represents a dimension or a specific attribute that describes the item. For our coffee shop, the dimensions were east-west position, north-south position, and altitude. For our recipe, they were flour quantity, sugar quantity, and egg quantity. In the world of vector search, we work with vectors that have many more dimensions, sometimes hundreds or even thousands. If you think of describing a person, you might use their height, weight, age, shoe size, and so on. Imagine assigning a number to each of these attributes. Now add attributes like their preferred color, their political leaning on a scale, their favorite type of music, etc. Each of these attributes can be a dimension. While we can't visualize a space with, say, 768 dimensions in our minds, a computer handles it just fine. It's still just a list of numbers, where each number helps to uniquely describe a complex entity. So, how do we get these complex things like text, images, or even sounds into the form of these number lists? This is where the magic of embeddings comes in. An embedding is the process, and the resulting vector itself, of transforming any piece of information, like that paragraph you just read, or a photo of a cat, or a recording of a song, into a numerical vector. This transformation isn't random. It's carefully crafted by advanced artificial intelligence models, usually a type of neural network. The goal of these AI models is to capture the meaning or essence of the original data in its numerical form. Think of it like this. You give a complex object, say, a spoken sentence, to a highly specialized machine. This machine then processes the sound waves, analyzes the words, understands the context, and ultimately spits out a carefully constructed list of numbers. These numbers, this vector, now represents the meaning of that sentence. If you feed a sentence with similar meaning into the machine, it will produce a vector that is numerically similar to the first one. Why go through all this trouble to turn everything into numbers? Because computers are brilliant at math. Once everything is a number, computers can then do some incredibly fast calculations to determine how close or similar two vectors are. If the AI model has done its job well, then two pieces of data that are semantically similar, like two sentences about large dogs, will produce vectors that are numerically close together in this high-dimensional space. Conversely, a sentence about fast cars would produce a vector that is far away from the large dog's vectors. This abstract space, where all these meaning-rich vectors live, is often called the embedding space or meaning space. In this space, all the recipes are grouped together, and within that group, all the cake recipes are even closer, and specific chocolate cake recipes are clustered even more tightly. The same applies to text, images, and any other data type. This concept of transforming diverse forms of information into a unified numerical meaning space is the bedrock of vector search. It's the invisible technology that allows computers to move beyond literal keyword matching and begin to genuinely understand the relationship and similarity between different pieces of information, enabling far more intelligent and intuitive search experiences. In the next chapter, we'll delve deeper into how these sophisticated embedding models actually perform this amazing feat of transformation for different types of data. Chapter 3. The Art of Transformation. How data becomes a vector. In our previous chapter, we established that vector search relies on turning all sorts of complex information like text, images, or even sounds into numerical lists called vectors. We also learned that these vectors are not just random numbers. They are carefully crafted so that similar pieces of data end up with similar vectors, positioning them close to each other in an abstract, meaning space. But how exactly does this miraculous transformation happen? How does a photograph of a cat or a paragraph about the American Revolution get condensed into a string of numbers that somehow captures its essence? The answer lies in highly sophisticated artificial intelligence models specifically designed for this purpose. You can think of these models as highly specialized black boxes or translators. You feed them a piece of raw data, and out pops its numerical vector representation. Just like you don't need to understand the intricate mechanics of how a coffee machine brews your morning cup, the water pressure, the heating elements, the precise timing, to appreciate the coffee, you don't need to delve into the complex mathematics or internal workings of these AI models to understand their crucial role in vector search. What's important is what they do and why it matters. These AI models are trained on vast amounts of data. During this training, they learn to identify patterns, relationships, and nuances within the data. For instance, an AI model trained on billions of sentences learns how words combine to form meaning, or how different objects typically appear in images. This learned understanding is then encoded into the vectors they produce. Let's explore how this transformation happens for different types of data. Text to vectors, unlocking language's meaning. Text is probably the most common type of data used in semantic search, and it's where many of the foundational concepts of embeddings originated. Early attempts to make computers understand text were quite primitive. They might simply count how many times a word appeared in a document. This worked for basic keyword matching, but it utterly failed at understanding meaning. For example, the sentence, "A furry companion makes life better," and "A domestic animal improves well-being," are vastly different in their exact words, but they convey a very similar idea. Simple word counting wouldn't recognize this semantic closeness. Then came the development of word embeddings. These models learned to represent individual words as vectors. The breakthrough idea was that words appearing in similar contexts often have similar meanings. For example, if the words cat and dog frequently appear near words like pet, fur, and play. Then the embedding model would assign them similar vectors. This allowed for interesting analogies. You could take the vector for king, subtract the vector for man, and add the vector for woman, and you'd often end up with a vector very close to queen. This showed that the vectors were capturing sophisticated relationships between words. However, individual word embeddings still couldn't fully capture the meaning of an entire sentence or paragraph. The word bank has a different meaning in river bank than in money bank. To solve this, sentence and document embeddings emerged. These more advanced models, conceptualized by techniques found in AI models like BERT or sentence transformers, don't just look at individual words. They analyze the entire sequence of words in a phrase, sentence, or even a whole document. They capture how words interact and influence one another within a given context. So, when you feed a sentence like a furry companion into such an embedding model, it produces a vector representing that entire phrase. If you then feed a domesticated feline into the same model, it will produce a vector that is incredibly close to the first one in our meaning space. But if you feed a car drives down the road, the resulting vector will be far, far away from the furry companion vector, because their meanings are entirely different. This is how these models allow a computer to understand that two different phrases mean essentially the same thing, or that they are entirely unrelated. Images to vectors. Seeing the world through numbers. Just as words are transformed into numerical representations of their meaning, so too can images. Visual embedding models learn to identify and represent the key features of an image. They don't just see a grid of pixels. They learn to recognize edges, textures, shapes, and eventually, objects and scenes. Imagine showing an image of a golden retriever playing fetch in a park to an image embedding model. This model, having been trained on millions, if not billions, of diverse images, will analyze the visual elements: the dog's fur, the green grass, the trees, the act of playing. It will then distill all of this visual information into a single vector. One of the most exciting developments in image embeddings are models that can place both images and text into the same meaning space. Take, for example, the conceptual process behind a model like CLIP, contrastive language image pre-training. When you input an image of that golden retriever playing fetch, it generates an image vector. Critically, if you then input the text description, a golden retriever playing fetch, into the text component of the same clip-like system, it will generate a text vector that is remarkably close to the image vector. This allows you to search for images using text descriptions or find text descriptions based on an image, directly recognizing their shared meaning. Other data types. The universal language of vectors. The power of embeddings isn't limited to text and images. Any type of data that contains meaningful patterns or relationships can be converted into vectors. Audio. Sound waves can be processed to extract features like pitch, tone, rhythm, and timbre, creating vectors that represent the sound's characteristics. This is used in applications like music recommendation, finding songs that sound like others, or identifying spoken commands. Videos are essentially sequences of images combined with audio. Models can analyze the visual frames for objects and motion, and the audio for speech or sounds, combining these features into vectors that represent scenes or actions. Tabular data, even structured data, found in spreadsheets or databases about customers, products, or financial transactions, can be vectorized. For instance, a customer's purchasing history, demographics, and browsing behavior can be distilled into a vector. Similar customer vectors might indicate similar interests or purchasing habits. The key takeaway is that these embedding models serve as advanced translators, converting the diverse, complex languages of human and digital information into the universal numerical language of vectors. This transformation is pivotal because, once data is in this numerical format, computers can then perform lightning-fast calculations to measure similarity, enabling the incredibly powerful and intuitive search experiences we'll explore in the coming chapters. The quality and sophistication of these embedding models directly dictate how intelligent and accurate your vector search system will be. Chapter 4. Measuring likeness. Understanding similarity metrics. We've learned that vectors are just lists of numbers representing data points, and that embeddings are the clever way AI models turn complex things like text and images into these vectors, ensuring that similar items end up with similar numerical fingerprints. Now, with all our data neatly transformed into these lists of numbers, a crucial question arises. How do computers actually measure how alike two of these numerical lists, or vectors, truly are? This is where similarity metrics come into play. These are mathematical formulas that quantify the closeness, or likeness, between two vectors in our abstract meaning space. They are the keys to unlocking the power of vector search, allowing a system to determine, for instance, that a picture of a tabby cat is more similar to an image of a ginger cat than it is to a picture of a dog, or that a query about outdoor adventure gear should return results for hiking boots and camping tents. Let's explore the two most common and intuitive ways of measuring this likeness. Cosine similarity, measuring direction of meaning. The most widely used similarity metric in vector search is called cosine similarity. It might sound intimidating, but the core idea is quite simple. It measures the angle between two vectors. Imagine two cars leaving a crossroads. One car heads directly north. Another car heads slightly northeast. These two cars are going in very similar directions, even if one drives further than the other. Cosine similarity works on the same principle. It doesn't care about the length of the vectors, how far the cars have traveled, but rather the angle at which they are pointing. In our abstract meaning space, if two vectors are pointing in almost the same direction, it suggests that the two pieces of data they represent share a very similar underlying meaning or theme. A small angle between them means high similarity. A large angle, pointing in opposite directions, means low similarity or even opposition. The value for cosine similarity typically ranges from -1 to 1. A value of 1 means the vectors are pointing in exactly the same direction. They are perfectly similar. A value of 0 means they are completely unrelated or perpendicular. A value of -1 means they are pointing in exactly opposite directions. They are opposites in meaning. For vector search, we usually look for values close to 1. For example, if the vector for large dog and the vector for small dog are very close in cosine similarity, it means they are both primarily about dogs. And that shared concept is dominant regardless of the large or small attribute. This metric is particularly good at capturing conceptual similarity, making it ideal for semantic search where the overall meaning, rather than specific magnitudes, is key. Euclidean distance. The straight line path. Another fundamental way to measure similarity is using Euclidean distance. This is much more intuitive because it's simply the straight line distance between 2 points in our numerical space. Think back to our city map analogy from Chapter 2. If you have 2 coffee shops plotted on the map, Euclidean distance would be the shortest straight line path between them. If coffee shop A is at 3, 5, and coffee shop B is at 4, 6, you can easily calculate the straight line distance. The shorter the distance, the closer the two shops are physically. In the context of vectors, a smaller Euclidean distance between two vectors means they are more similar to each other. Unlike cosine similarity, Euclidean distance does consider the magnitude of the vectors and can be influenced by the scale of the numbers. When would you use Euclidean distance? It's often preferred when the absolute values or specific attributes encoded in the dimensions are particularly important, and where a perfect match on all attributes makes two items truly closer in a measurable sense. For instance, if you're comparing customer profiles where specific numerical traits like age, income, and number of purchases are key, Euclidean distance might better capture their overall numerical proximity. Other metrics and considerations. While cosine similarity and Euclidean distance are the most prevalent, other metrics exist, such as the dot product, which is closely related to cosine similarity. The choice of which metric to use often depends on the specific problem, the nature of the data, and how the embeddings themselves were constructed. Sometimes, a combination of factors is used. The crucial point is that by converting complex data into numerical vectors, we enable mathematical comparisons. These similarity metrics provide a quantifiable way for computers to understand likeness directly from those numerical representations. This means when you search for a tranquil painting of a lake, Your query vector is compared using one of these metrics against millions of painting vectors, allowing the system to instantly surface those whose numerical fingerprints indicate a high degree of semantic closeness. Without these metrics, the powerful embedding models would simply be producing lists of numbers with no way to meaningfully compare them. They are the mathematical tools that transform the abstract concept of similarity of meaning into concrete, computable values, laying the groundwork for the incredibly fast and intelligent search capabilities we'll explore next. In the next chapter, we'll tackle the challenge of how computers can perform these similarity measurements at scale, sifting through billions of vectors in mere milliseconds. Chapter 5. The Search Engine's Speed Secret, High-Dimensional Indexing. We've now seen how powerful it is to turn data into vectors, and how similarity metrics like cosine similarity can accurately measure the likeness between them. This semantic understanding is indeed a giant leap beyond keyword matching. But there's a massive challenge lurking in the background: scale. Imagine an online store with 1 billion products, each represented by a vector, or a social media platform with a constantly growing library of trillions of images and videos, all vectorized. When you submit a query, say, a picture of a vintage car, how does the system find similar pictures among those billions of items? The intuitive approach for a computer would be to take your query vector and compare it one by one to every single vector in its database. This is called a brute force search. On a small scale, it works. But with billions or trillions of vectors, this approach quickly becomes impossibly slow. Even a powerful computer would take hours, days, or even weeks to churn through all those comparisons for a single search query. In our grand, messy library analogy, this would be like having to physically pick up and read the blurb of every single book in the building to find the one you want. Clearly, this won't work for anything requiring real-time results. This is the great challenge of vector search: how to find the nearest neighbors, the most similar vectors, efficiently and quickly in a massive, high-dimensional space. The solution lies in a set of ingenious techniques known as approximate nearest neighbor, ANN, search algorithms, and their role in high-dimensional indexing. The approximate advantage: good enough, fast enough. The key insight behind ANN search is the word approximate. In most real-world scenarios, we don't need the absolute perfect, mathematically closest vector in billions. We just need a very good set of results that are highly relevant and retrieved in milliseconds. Think about it like this. If you're looking for a good pizza place near your current location, you probably don't need to calculate the precise GPS coordinates and driving distance to every single pizzeria in your entire city to find the single closest one. You just need a few good options that are conveniently nearby. ANN algorithms do something similar. They sacrifice a tiny, almost imperceptible amount of accuracy. They might miss the absolute best match, but they'll get one that's 99.9% as good in favor of incredible speed. Indexing, organizing the meaning space. To achieve this speed, vectors can't just be stored randomly. They need to be organized, or indexed, in a special way that allows the system to quickly narrow down the search space. This is akin to how a librarian might organize books, not just in one giant pile, but by subject, author, publication date, or a combination of these. When you ask for a specific book, the librarian doesn't check every book. They go straight to the relevant section. ANN algorithms create these intelligent indexes for vectors. They group similar vectors together, allowing a search query to quickly home in on the most promising neighborhoods of the meaning space, rather than having to scan the entire landscape. Let's look at some conceptual ways these indexing algorithms work. One-tree-based methods, e.g., ANOI, KD trees, conceptually. Partitioning the space. Imagine you have a large backyard, and you want to organize all your garden tools. You might decide to group them by type, shovels here, rakes there, and then within each type, by size. Tree-based indexing algorithms apply a similar idea by recursively dividing the high-dimensional space. They build a tree structure where each branch represents a partition of the vector space. When you search, the algorithm traverses the tree, making decisions at each fork to go down the branch that is most likely to contain the nearest neighbors. It effectively ignores entire vast sections of the space that are unlikely to contain relevant results. While conceptually simple, These methods can become less efficient in very high dimensions, where the curse of dimensionality makes it hard to effectively partition space. 2. Graph-based methods, e.g., HNSW hierarchical navigable small world, building a network of connections. These are currently among the most popular and performant ANN algorithms. Imagine each vector in your database is a person in a social network. Each person is directly connected to a few of their closest friends, i.e., highly similar vectors. Now, imagine some people also have connections to a few more distant acquaintances. Graph-based algorithms build a network, or graph, where vectors are nodes and edges connect neighboring, similar vectors. When a query comes in, the search starts at a random point in this graph and then walks through the connections, always moving towards vectors that are closer to the query. HNSW takes this a step further by creating multiple layers, a hierarchy of these graphs. The top layers are very coarse, with broad connections, acting like a highway system to quickly get you into the right general area. The lower layers are much denser, like local roads and footpaths, allowing for very precise fine-tuning once you're in the right neighborhood. This hierarchical structure allows for incredibly fast navigation across vast numbers of vectors. It's like finding a book by first going to the right floor of the library, then the right aisle, then the right shelf. 3. Quantization methods, e.g., product quantization, LSH conceptual. Compressing for speed. Another strategy involves compressing or quantizing the vectors themselves. Think of it like taking a very detailed, high-resolution photograph and creating a smaller, lower-resolution version. It loses some detail, but it's much faster to store, transmit, and compare. Quantization methods essentially compress the high-dimensional vectors into shorter, more compact representations. Comparing these compressed vectors is much faster than comparing full-sized ones, and it uses less memory. Locality-sensitive hashing, LSH, is another approach that maps similar items to the same buckets, making quick comparisons possible. While there's a slight loss of precision, the speed gains are enormous. The speed-accuracy trade-off. A crucial aspect of all ANN algorithms is the inherent trade-off between search speed and memory usage and accuracy. If you demand absolute perfect accuracy, you often have to slow down the search or use more memory. If you prioritize lightning-fast results, you might accept a tiny drop in search accuracy, but the results will still be highly relevant for practical purposes. Engineers deploying vector search systems carefully calibrate these algorithms to achieve the optimal balance for their specific application. For an e-commerce recommendation system, getting 99% of the best matches in 50 milliseconds is far more valuable than getting 100% in 5 seconds. These high-dimensional indexing and ANN algorithms are the unsung heroes of vector search. They are the intricate engines that allow systems to sift through oceans of vectorized data in fractions of a second, making truly semantic understanding a practical reality for the massive, ever-growing datasets of our digital world. With this indexing power, we can now effectively search. But what happens from the moment you type your query to the instant you see results? That's what we'll explore next. Chapter 6. Making sense of the query. From input to insight. We've now covered how data transforms into vectors, how we measure their likeness, and the clever indexing tricks that let computers scan billions of these vectors in milliseconds. But how does this all come together when you, the user, want to find something? What happens from the moment you type a search query or upload an image until you see the relevant results? This chapter walks through that exciting journey. Let's imagine you're on an online clothing store and you type, "comfortable, breathable running shoes for hot weather." Or perhaps you're on a stock photo site, and instead of typing, you upload a picture of a vibrant, tropical sunset, hoping to find similar images. In both scenarios, your input, your query, embarks on a transformation journey to find its semantic matches. Vectorizing the query, entering the meaning space. The very first and most crucial step is that your query itself must also be transformed into a vector. It needs to speak the same numerical language as all the items indexed in the database. Here's the critical detail. The system uses the exact same embedding model to vectorize your query as it used to vectorize all the products, images, or documents in its database. Why is this so important? because it ensures that your query vector is placed into the same meaning space. If you used a different embedding model, it would be like trying to find a street on a map of New York City using the coordinates from a map of London. Nothing would line up correctly. So, when you type comfortable, breathable running shoes for hot weather, the text immediately goes into the text embedding model. That model processes the words, understands their collective meaning, and outputs a single vector representing your specific query. Similarly, if you upload a picture of a tropical sunset, that image is fed into the image embedding model, which then spits out a vector for the sunset picture. Now, your query, whether text or image, has been distilled into a high-dimensional numerical fingerprint. It has officially entered the meaning space. The search, finding the nearest neighbors. Once your query is a vector, the real search begins. This query vector is then sent to the specialized vector index we discussed in Chapter 5. This index, remember, is like a highly organized digital map of all the other millions or billions of item vectors. The approximate nearest neighbor, ANN, algorithm within the index takes your query vector and efficiently navigates through this map. Its goal is to find the nearest neighbors, the item vectors that are numerically closest to your query vector in that high-dimensional space. Closeness, in this context, directly translates to semantic similarity, as measured by metrics like cosine similarity. So, for your comfortable, breathable running shoes for hot weather query, the system quickly finds vectors representing shoes that are not just running shoes, but specifically those known for being lightweight, airy, and suitable for warm climates. It doesn't matter if the product description used the exact words, breathable or hot weather. If the meaning encoded in its vector is close to your query's meaning, it will be found. Similarly, your tropical sunset image query will pinpoint other images whose vectors indicate similar themes. Vibrant colors, specific types of clouds, palm trees, or ocean views, regardless of what exact keywords might have been tagged to them, or even if they had no tags at all. Result retrieval and ranking. Once the ANN algorithm identifies the top K, a predetermined number, like 10 or 100 most similar vectors, the system then retrieves the original data associated with those vectors. These are typically the product descriptions, image files, or document contents that you can actually see and interact with. These results are then ranked, usually by their similarity score to your query vector. The closer the match, the higher it appears in the search results. Refining results with filters and metadata. While vector search excels at understanding the meaning behind your query, sometimes you need to add specific, factual constraints that don't inherently carry meaning in the same way. For instance, you might want those running shoes to be size 10 and under $100. This is where traditional filters and metadata come into play. Alongside the vectors, systems often store descriptive information about each item, such as its price, size, brand, color, publication date, or any other specific attributes. There are generally two ways these filters are applied. Post-retrieval filtering. The vector search first retrieves the top and semantically similar results. Then, these end results are filtered down based on your additional criteria, e.g., only show size 10 shoes. This gets you semantically relevant items, then narrows them down factually. Hybrid approach, pre-filtering, or combined search. More advanced systems might integrate the filtering earlier in the process. For example, the system might first identify all products that are size 10 and under $100, and then perform a vector search only within that subset. Or, the vector database itself might allow for combined semantic and metadata-based filtering queries, making the search even more precise from the outset. Regardless of the exact implementation, the combination of powerful semantic understanding from vector search and precise filtering using metadata allows for incredibly flexible and accurate information retrieval. The journey from your initial thought or image to seeing relevant results is a seamless interplay between cutting-edge AI models, sophisticated indexing algorithms, and the fundamental principle of numerical similarity. This entire pipeline, from raw data to your screen, constitutes a complete vector search system, and that's what we'll tie together in the very next chapter. Chapter 7, The Vector Search Pipeline, a journey from data to discovery. By now, we've disassembled the engine of vector search, examining its powerful, individual components. The ability to turn anything into a numerical vector, embeddings, the mathematical tools to measure their likeness, similarity metrics, and the clever indexing strategies that make searching billions of these vectors lightning-fast ANN algorithms. We've also traced the path of a single query as it transforms and seeks its matches in the meaning space. Now, it's time to put all those pieces back together. Imagine a sophisticated assembly line where raw materials enter at one end, undergo several precise transformations, and finally, a perfectly tailored product emerges at the other. That's conceptually what a complete vector search system, or pipeline, looks like. A continuous flow designed to transform raw information into actionable insights. Let's trace the journey, step by step, from the moment original data comes into existence to the point where a user receives intelligent results. 1. Data ingestion, the raw ingredients. Every vector search system begins with data. This could be anything. The full text of millions of articles from a news archive, product descriptions and images from an e-commerce website, video clips from a security camera network, snippets of audio from customer service calls, or even complex scientific datasets. This stage involves collecting this raw information. Often, it also includes pre-processing or cleaning the data. For instance, removing irrelevant formatting from text, compressing large image files, or transcribing audio into text. The goal here is to prepare the data for the next crucial step, turning it into something the AI models can understand. 2. Embedding generation, the numerical transformation. Once the data is pre-processed, it enters the embedding generation stage. This is where the magic, or rather, the sophisticated AI models happens. Each piece of data, be it a paragraph, an image, a video frame, or an audio clip, is fed into its respective, pre-trained embedding model. The model analyzes the data and produces its numerical fingerprint, the high-dimensional vector. For example, every product description on an e-commerce site might get its own vector, and every product image might get a separate image vector or a combined multimodal vectors. This process typically runs continuously as new data is added or old data is updated. These vectors are the core currency of our meaning space. 3. Indexing, organizing the meaning map. With vectors in hand, the next step is to make them searchable. This is where the indexing component comes into play. The generated vectors are ingested into a specialized vector database or an in-memory approximate nearest neighbor, ANN, index. Recall that this index doesn't just store the vectors. It organizes them in a clever way, using methods like HNSW graphs or tree structures to enable incredibly fast retrieval later. It's like meticulously categorizing and cross-referencing every single book in that vast library. So when a query comes, you don't have to search every shelf. This index building process is vital for the speed and efficiency of the overall system. It often involves a lot of computational power, but it's done only once for a given batch of data or incrementally as new vectors arrive. 4. Query processing, the user's request. Now the system is ready for action. A user initiates a search. This could be typing a natural language question into a search bar. What's the best hiking trail for beginners in the Rocky Mountains? Uploading an image, find me similar dresses, or even speaking a voice command. Just like the data in the database, this raw user query must also be transformed into a vector. It is fed into the same type of embedding model that was used to create the vectors in the index. This ensures the query vector lands squarely within the same meaning space as the stored data, allowing for meaningful comparisons. 5. Vector search, ANN lookup. The semantic matchmaker. The user's embedded query vector is then sent to the vector index. This is where the ANN algorithm, the semantic matchmaker, performs its core function. It quickly scours the high-dimensional space, navigating through its optimized graph or tree structures to identify the most similar vectors to the query vector. The output of this stage is a list of database identifiers, IDS, corresponding to the data items whose vectors were deemed the closest matches. These IDS are essentially pointers back to the original information. 6. Result retrieval and ranking, from IDS to insight. Finally, armed with the IDS of the top matching vectors, the system retrieves the original, human-readable data items associated with those IDs. For instance, if the vector search returned IDs for product descriptions, the system fetches those full descriptions, images, and pricing information. These retrieved results are then ranked based on their calculated similarity scores, e.g., cosine similarity to the query vector, with the highest scoring items appearing first. This is also the stage where any additional filters, like price under $100 or stock available, are applied to further refine the results before they are presented to the user. This six-stage pipeline operates continuously. As new data streams in new products, updated articles, fresh images, it's ingested, converted into embeddings, and added to the index, keeping the system up to date. When a search query arrives, it flows through the query processing, vector search, and result retrieval stages, delivering an intelligent response often in mere milliseconds. The beauty of this pipeline is its modularity and scalability. Each stage can be optimized independently, and the entire system can handle immense volumes of data and queries. This robust framework is what allows vector search to underpin so many of the intelligent applications we encounter every day. In the next chapter, we'll dive into concrete examples of how this pipeline is put to work in the real world, powering features you likely use without even realizing it. Chapter 8, Real-World Impact, Case Studies and Applications. We've now dismantled and reassembled the vector search pipeline, understanding how data becomes meaningful numbers, how likeness is measured, and how billions of these numbers can be searched in an instant. The question then becomes, where is all this powerful technology actually used? The truth is, vector search is already a quiet, foundational force behind many of the intelligent features we encounter daily, often without even realizing it. It's working behind the scenes, making our digital lives more intuitive and efficient. Let's explore some compelling real-world applications where vector search moves beyond theoretical concepts to deliver tangible value. 1. E-commerce, intelligent product discovery and recommendations. Imagine shopping online. You might type a specific product name, but often you have a more abstract need. I need comfortable walking shoes that are good for long distances and stylish enough for city wear. A traditional keyword search might struggle to balance those conflicting needs, showing you either highly ergonomic but ugly shoes or stylish but uncomfortable ones. How vector search helps. Semantic product search. Every product description, image, and customer review can be turned into a vector. When you type your nuanced query, it also gets vectorized. Instead of matching words, the system matches the meaning of your request to the meaning encoded in the product vectors. It can surface shoes that customer reviews describe as like walking on clouds, a semantic match for comfortable, even if the word comfortable isn't explicitly in the product title. Intelligent recommendations. Customers who bought X also bought Y is useful, but vector search can go deeper. It can recommend products that are semantically similar to what you've browsed or purchased, even if they're in different categories. If your vector indicates an interest in sustainable, eco-friendly outdoor gear, the system might recommend a reusable water bottle, a solar-powered charger, or recycled fabric clothing, based on the shared semantic threads captured in their vectors. Case study, finding the perfect coffee maker. A user searches for espresso machine with milk frother, easy to clean for home use. A traditional search might just look for espresso. Frother. Vector search understands the implicit value of easy to clean, perhaps by identifying products whose reviews contain phrases like simple maintenance or dishwasher-safe parts, and for home use, filtering out commercial-grade machines based on price, size, or power, all of which might be encoded in the product's vector. The result is a highly relevant set of options. 2. Generative AI and chatbots, retrieval augmented generation, RAG. Large language models, LLMs, like those powering sophisticated chatbots, are incredible at generating human-like text. However, they sometimes hallucinate, make up facts, or are limited by their training data's cutoff date. For factual accuracy and real-time information, they need help. How vector search helps RAG, grounding LLMs in reality. When you ask a chatbot a question, especially one requiring up-to-date or proprietary information, e.g., what's my company's policy on remote work? The chatbot doesn't just think. Instead, your question is first converted into a vector. Smart document retrieval. This query vector is then used to perform a vector search against a database of vectorized company documents, knowledge base articles, or up-to-the-minute news. The vector search quickly identifies the most semantically relevant snippets of information. Informed response generation. These retrieved, factual snippets are then fed alongside your original question to the LLM. The LLM then uses this retrieved information to formulate a precise, accurate, and contextually relevant answer, significantly reducing hallucinations and ensuring the information is current. This makes chatbots far more reliable and useful in practical applications, preventing situations where they might invent policies or use outdated medical advice. 3. Image and video search. Seeing beyond keywords. Searching visual content with text has always been challenging. How do you describe a specific scene or object if you don't know the exact keyword? How vector search helps. Content-based visual search. Images and video frames are transformed into vectors that capture their visual composition. You can then search for images using other images, e.g., show me more photos like this one of a mountain lake at sunset. Or, critically, using natural language descriptions, find all videos showing someone riding a bicycle down a winding path. The system doesn't need pre-existing tags or metadata. It understands the visual content itself. Specific scene or object retrieval. In vast media archives, a broadcaster might need to find all footage of a politician shaking hands with constituents from 2023. Each video segment can be vectorized to describe its content, allowing for highly granular searches. Application example. A stock photo website lets you upload an image of a red vintage car. The system instantly returns similar images, not just red cars or vintage cars, but vehicles with similar styling, era, and even background, because its vector recognized the visual nuances. 4. Anomaly detection. Spotting the unseen deviations. In fields like cybersecurity, fraud detection, or industrial monitoring, vector search can identify unusual patterns that signify problems. How vector search helps. Behavioral fingerprinting. Normal user behavior, network traffic patterns, or machine sensor readings can be vectorized. These normal vectors will cluster closely together in the meaning space. Outlier identification. An operation or data point that significantly deviates from the norm will produce a vector that is far away from the clusters of usual behavior. Vector search can quickly flag these distant, anomalous vectors. Example: financial fraud. A customer's typical transaction patterns, amount, location, frequency are vectorized. If a new transaction comes in whose vector indicates a highly unusual pattern, e.g., a large purchase in a foreign country after a long period of inactivity, its vector will be a distant outlier, triggering a fraud alert. 5. Customer support, streamlining service and knowledge access. For large organizations, directing customer queries or helping support agents find information quickly is critical. How vector search helps. Intelligent call chat routing. When a customer describes their issue, "My internet is constantly disconnecting and my router lights are flashing red," their complaint is vectorized. This vector is then matched against vectors representing different support team specializations or common issue types, routing the customer to the most qualified agent or self-help resource. Semantic knowledge base search. Customer support agents often need to quickly find solutions in vast knowledge bases. Instead of guessing keywords, they can type a natural language question or even paste snippets of a customer conversation. Vector search instantly pulls up the most relevant articles or troubleshooting guides, even if the phrasing doesn't precisely match. These examples are just the tip of the iceberg. From bioinformatics, finding similar protein structures based on their vectors for drug discovery, to content moderation, identifying harmful or unsuitable content in large datasets. Vector search is fundamentally changing how we interact with, understand, and leverage vast amounts of digital information. It's a powerful testament to how moving beyond literal interpretations to a deeper understanding of meaning can unlock unprecedented capabilities across virtually every industry. Chapter 9: The Road Ahead. Challenges and Future of Vector Search. We've now journeyed through the intricacies of vector search, from turning data into numerical fingerprints to organizing billions of them for lightning-fast retrieval. It's clear that this technology is a paradigm shift, enabling machines to understand meaning in ways previously unimagined. However, like any rapidly evolving field, vector search is not without its current limitations and exciting future frontiers. Understanding these challenges is crucial, as they are the very problems driving the next wave of innovation. Current limitations and active research areas. 1. Scalability. The ever-growing ocean of data. While approximate nearest neighbor, ANN, algorithms are remarkably efficient, pushing the boundaries to truly massive scales, trillions of vectors, constantly updating presents significant engineering challenges. Storing, processing, and indexing such immense datasets requires vast computational resources, including high-performance servers and copious amounts of memory. Improving the efficiency of these indexes, reducing their memory footprint, and developing novel distributed architectures to handle unimaginable volumes of data remain active areas of research and development. It's an ongoing race to keep pace with the explosion of digital information. 2. Explainability, the why behind the what. One of the biggest challenges, not just for vector search but for much of modern AI, is explainability. When a vector search system returns a list of results, it does so because the vectors were mathematically close. But for a human user, simply stating it's a close vector can be unsatisfying. Why, specifically, was this news article considered relevant to my query, even if it didn't use my exact keywords? What aspects of the image made it similar to my uploaded photograph? Providing transparent, human-understandable reasons for a search result is crucial for building trust, and for debugging systems when they make mistakes. Research is focused on developing methods to highlight the specific features or dimensions of a vector that contributed most to its similarity, effectively offering a rationale behind the semantic match. 3. Bias, the mirror of our world. Embedding models learn their understanding of the world from the data they are trained on. Unfortunately, if that training data contains existing societal biases, for instance, stereotypical associations of certain professions with specific genders or ethnicities, these biases can be inadvertently encoded into the embeddings. This means that a vector search might return results that reflect and even amplify those biases. For example, if an embedding model is trained on text where doctor is predominantly associated with male pronouns, a search query for successful doctor might unintentionally yield results that are disproportionately male, even if the underlying dataset contains many successful female doctors. Addressing and mitigating these biases in embedding models and the search process is an incredibly important area of ethical AI research, ensuring that vector search systems are fair and equitable. 4. Real-time updates. Keeping information fresh. Many datasets are dynamic, constantly changing. News articles are published every minute, product prices fluctuate, social media feeds update by the second. Keeping a vector index perfectly synchronized with this real-time flow of new and updated information is complex. Rebuilding an entire index from scratch every time new data arrives is computationally prohibitive. Researchers are working on techniques for incremental indexing, allowing new vectors to be added efficiently without disrupting ongoing searches, and for swiftly addressing changes or deletions of existing data. Emerging trends and what's next. Despite these challenges, the field of vector search is vibrant and accelerating, pushing into exciting new territory. 1. True multimodal search. While we touched upon image-to-text search, the future points towards seamless, integrated multimodal understanding. Imagine a query like, find videos of a dog playing with a toy like the one in this picture, where the owner is giving commands similar to this audio clip. This requires creating unified embedding spaces where text, images, audio, video, and even structured data can all be represented and searched together, creating a holistic understanding of complex information. 2. Specialized vector databases, vector DBMS. Until recently, vector search capabilities were often added as a layer on top of traditional databases or used through standalone libraries. However, a new category of vector databases, or vector database management systems, is emerging. These are purpose-built from the ground up to store, index, and query vectors natively and efficiently, integrating all the necessary components like ANN algorithms and metadata filtering directly into their core architecture. This specialization promises even greater performance, scalability, and ease of use. 3. Personalization and adaptation. Future vector search systems will likely become even more intelligent by adapting to individual user preferences and feedback. By observing which results a user clicks on, how long they view them, or even their explicit likes and dislikes. The system can subtly refine their query vector or re-rank results to deliver an even more personalized and intuitive search experience over time. 4. Edge and on-device AI. As embedding models become more compact and efficient, it's becoming feasible to perform vector search directly on user devices, such as smartphones, smart speakers, or IoT devices. This brings benefits like enhanced privacy. Data doesn't need to leave the device, lower latency, no cloud round trip, and offline capabilities. Imagine a personal image gallery on your phone that can instantly find all pictures of sunsets without sending them to a server. 5. Continual learning and evolving embeddings. Embedding models typically require massive, one-time training. However, the world changes and new concepts emerge. Research is exploring continual learning for embeddings, allowing models to adapt to new information and evolving meanings without needing to be fully retrained from scratch. This ensures that the meaning space remains relevant and up-to-date with the ever-changing landscape of human knowledge and data. The challenges we face in vector search are not roadblocks. They are signposts pointing to the next breakthroughs. The field is a dynamic frontier where new algorithms, models, and system architectures are constantly being innovated. This continuous evolution means that the intelligent future, powered by semantic understanding, is not a distant dream, but an ongoing construction built on the foundations we've explored in these pages. Chapter 10. The Intelligent Future, Embracing Semantic Understanding. We have now journeyed through the intricate world of vector search, pulling back the curtain on a technology that is quietly, yet profoundly, reshaping our digital landscape. We began by grappling with the limitations of traditional keyword search. Its struggles with nuance, its inability to grasp context, and the sheer frustration it can cause when our intent isn't literal. We then peeled back the layers of vector search, revealing its core components. Vectors and embeddings, the ingenious way data, whether text, images, or sounds, is transformed into precise numerical fingerprints, capturing its underlying meaning in a high-dimensional space. Similarity metrics, the mathematical tools like cosine similarity that quantify how alike these numerical fingerprints are, translating numerical closeness into semantic relevance. High-dimensional indexing, ANN, the clever algorithms and data structures that allow us to sift through billions, even trillions of these vectors in milliseconds, making semantic search at scale not just possible, but exceptionally fast. The vector search pipeline, the elegant orchestration of all these components into a seamless flow, from raw data ingestion to intelligent result delivery. Real-world impact. Concrete examples of how this technology is already powering everything from hyper-personalized e-commerce recommendations and accurate AI chatbots to sophisticated image recognition and fraud detection systems. The recurring theme throughout this exploration has been the fundamental shift from literal matching to semantic understanding. No longer are we constrained by the exact words typed or the precise tags assigned. Instead, vector search empowers systems to interpret the meaning behind our queries and the essence of the data itself. This deep understanding of meaning is not just a technical upgrade. It's a foundational pillar for the future of artificial intelligence and information access. Vector search is not just a component of modern AI. For many applications, it is the intelligence layer that allows machines to interact with the world in a way that feels natural and intuitive to humans. It's what enables a chatbot to accurately answer a complex question by referencing millions of documents, or a smart photo album to find every picture of a joyful family gathering regardless of specific tags. This technology is redefining the very nature of our interaction with data. We are moving beyond the cumbersome act of learning how to search for the machine and towards a future where the machine learns how to understand us. The friction of trying to find things in a vast digital ocean is being reduced significantly because the underlying systems can now grasp context, synonyms, and the subtle relationships between concepts. This makes information more accessible, more relevant, and ultimately more useful. The societal impact of truly semantic search is profound. It enhances discovery in every field, from scientific research and medical diagnostics, where finding obscure but relevant papers can accelerate breakthroughs, to legal discovery, where sifting through mountains of documents for conceptual relevance is critical. It democratizes access to information by making it easier to find what you need, even if you don't know the precise terminology or linguistic conventions. It fuels innovation by providing a powerful way to organize and extract insights from the ever-growing deluge of data. Of course, as we briefly explored, this powerful capability comes with responsibilities. Addressing bias in embedding models, ensuring explainability, and maintaining the privacy and security of increasingly detailed vector data are critical challenges that the industry must and is actively working to overcome. These are not hindrances to progress, but guiding principles for building an intelligent future that is equitable and trustworthy. So, what might a world deeply integrated with vector search look like? Imagine a future where your digital assistants genuinely anticipate your needs, not just reacting to commands. When you plan a trip, they seamlessly synthesize information on weather, local cuisine, historical sites, and flight deals, understanding the subtle connections between your expressed interests. Learning becomes even more personalized and intuitive. Educational platforms understand your style of learning and provide resources, text, video, interactive simulations that resonate most effectively with you, identifying concepts that are semantically similar to what you already grasp and connecting them to new knowledge. Creative processes are supercharged. Artists, designers, and writers can pull inspiration from vast libraries of images, sounds, and text snippets, searching by mood, conceptual similarity, or abstract relationships that transcend keywords. Every enterprise operates with unprecedented efficiency, with employees finding the exact information they need from internal documents, customer interactions, and market trends, irrespective of how the data is filed or phrased. Vector search is more than just an engineering feat. It represents a philosophical shift in how we approach information. It acknowledges that meaning is fluid, contextual, and often implicit, and that our digital tools must reflect this complexity. It is the engine driving our transition from an information age, burdened by data overload, to an insight age, where understanding is paramount. The journey beyond keywords is well underway. As vector search continues to evolve and integrate even deeper into our technological fabric, it promises a future where our digital interactions are not just faster or more convenient, but truly intelligent, intuitive, and profoundly meaningful. The ability to understand is, after all, the ultimate power,